Sometimes chemistry concepts get lost in all the math, complicated names, and formulas. Don't let the big words trip you up. There's reason to the madness. Imagine you have a pool, and you want to know how many gallons of water in the pool. How can you figure it out? You could make a qualitative estimate and say, a lot, but we can do better than that. A quantitative measurement would be better because we could have an actual number. You could slowly drain and measure all the water in the pool, being careful not to spill anything, of course. You could weigh the water as you remove it and then convert that to gallons based on the density, but that might take a while. Or you could make an estimate based on the length, the width, and the depth of the pool. When you estimate something, you lose some precision, like you estimate the number of jelly beans in a jar. You may use a lot of measurements to make a scientific estimation, but you could still be off by a few beans. When we estimate the size of a pool, we'll use a certain level of precision. We could measure in feet, which is sort of vague, inches, which is more precise, or millimeters, which is even more precise. You could even use calculus to find the volume of the curved regions, but maybe that's more precise than you have time for. Instruments that measure with more vague increments are said to have fewer significant figures than instruments with more specific increments. For example, if we measure the length of the pool, we know how many meters there are, 10, plus an estimated digit, 7. We have 3 significant figures. If I measure in centimeters, I have the number of centimeters, 1,074, plus an estimated digit, 0.6. In this case, there are 5 significant figures. If I measure in millimeters, I have 10,746, plus an estimated digit of 0.3. And therefore, I have 6 significant figures. More precision means more significant figures. Here's the thing, though. When you measure with instruments that have different significant figures, you have to dumb it down to the tool with the least sig figs. That's because the estimated value is so vague that it washes out how specific the other measurements are. Let's use the pool as an example. If you measure the length with a meter stick and the width with a millimeter stick, you can only use the number of significant figures that the meter stick has, because it has the least precise measurement. If you wanted to have more sig figs, then measure both sides with the millimeter stick. If I end up estimating that the pool has 35,600 gallons, this number is not really that specific. The most specific digit is the 6. That means that the 600 was actually an estimated number. It could really be more than 600 or less than 600, but this estimate wasn't that specific, so even if I add a gallon of water to the pool, I still have 35,600 gallons. That's because 1 gallon doesn't come anywhere close to the hundreds of gallons area where my estimate ended. The 1 gallon is too specific and small to make a difference. It's insignificant. So we ignore it and sacrifice it to the significant figures gods. Let's go through the rules of significant figures in order to find where the estimation should end. I use the United States as a way to remember how sig figs work, partly because I have an Amerocentric habit, but also because the names of the oceans work out really nicely. The Pacific Ocean and the Atlantic Ocean. P means the decimal is present, A means the decimal is absent. All numbers other than 0 always count. Zeros only count between non-zeros or after a decimal and after a non-zero number. Let's see a few examples. Take 2.20. A decimal is present, so we start counting from the Pacific side. Any non-zero counts, and the 0 counts in this case because it's after a non-zero number that's after a decimal. There are 3 sig figs. But what about the number 220? The decimal is absent, so count from the Atlantic side. The first sig fig can never be a 0, so in this case there are only 2 sig figs. What about 0.00220? A decimal is present, so start from the Pacific side. Again, the first sig figs can't be a 0, so the first sig fig is the 2. But the last 0 counts, because it's after a non-zero number and after the decimal. There are 3 sig figs. If it's hard to see why the first zeros don't count, just rewrite the number in scientific notation and it becomes clear. Now you're ready for the calculation rules. For multiplication and division, do the math first, then round your answer to the lowest number of significant figures. 275 times 45, do the math first. Then identify which number had the least number of sig figs, and round your answer to 2 sig figs. The 3 is less than 5, so the answer will stay at 12,000. Remember, those zeros after the 12 are not significant. They're just placeholders so that you know you have 12,000 instead of 12. This answer has 2 sig figs. 4,000 divided by 9. Do the math first. Then find the least number of sig figs. In this case, both numbers only have 1 sig fig, so we round our answer to 1 sig fig, which leaves us with 400. When you want to add or subtract, the rules are similar but with a slight change. Line up the decimals, do the math, then round to the least specific digit. Here's an example. 27.2 plus 2.145. Line up the decimals, do the math first, Then find the least specific digit. In this case, it's at the point 2. Round to that position. The answer is 29.3. Here's subtraction. 38 minus 4.16. Line up the decimals, do the math, find the least specific digit, which is the ones place, and in this case we round up because 8 is higher than 5, so our answer is 34. One last example, 20,000 plus 3.12. First, line up the decimals, do the math, then find the least specific digit, which in this case is in the 10,000s place, and round. Well, the answer is 20,000. This is like the pool problem. The 3.12 is so tiny, so small, that it's insignificant in comparison to the estimated number of 20,000. Dimensional analysis might actually be one of my favorite things in the world. Really, I'm being serious. With dimensional analysis, you can figure out how many elephants lined up end to end it would take to get to the moon, because you totally need to know that. How many seconds of your life are spent sleeping, how many formula units of chalk are needed to write your name on a chalkboard. It's awesome. Here's the basic idea. Any number multiplied or divided by 1 is still equal to the original number. You could even say 12 times 3/3 equals 12. And 12 divided by 3/3 equals 12. That's because 3 and 3 are equal to each other, and therefore are equivalent to 1. Now take a conversion, like 12 inches equals 1 foot. You could have 2 feet or 24 inches, and that measurement is still the same. They are equal in the same way that 3/3 was equal to 1. So, you can write the equal sign like a division sign and read it 12 inches per foot. But you could also write it the other way, and it would still be true, 1 foot per 12 inches. This is called a conversion factor, and it's the crux of dimensional analysis. Conversion factors allow you to change from one unit to another, and so on until you get the units that you want. So let's try an example problem. How many decades are in 5 centuries? Start with what you're given, 5 centuries. Next, in order to get rid of the current unit, centuries, we have to cancel it with the same unit on the bottom of the next conversion factor. Next, you think of the relationship between centuries and something smaller. In 1 century, there are 100 years. The units of centuries are equivalent, so we can ignore them by crossing them out. Now we need to get rid of years, so put years on the bottom of the next conversion factor and think of the relationship between years and decades. 10 years makes 1 decade. Years cancel. And all that's left is decades. Now just multiply any number on the top and divide any number on the bottom. 5 times 100 times 1 divided by 1 divided by 10, the answer is 50 decades. Now you don't really need to put the ones in your calculator, but make sure the numbers on top are multiplied and the numbers on the bottom are divided. Let's try another. How many milligrams of lead are in 0.078 kilograms of lead? First, you need to know your metric prefixes. I use the mnemonic, King Henry died unexpectedly drinking chocolate milk. To remember, kilo, hecto, deca, the unit, meters, liters, or grams, deci, centi, and milli. These decrease by a factor of 10 as you go from left to right. Start with what you're given, 0.78 kilograms of lead. You know that you're going to need to put kilograms of lead on the bottom in order to cancel the unit. And we're trying to get to milligrams of lead. Whichever unit is larger will get the value of 1. Now we just need to see the relationship between the kilogram and the milligram. So starting over at kilo, which is the largest, we're going to see how many times we have to move over to get to milli. Each time represents a factor of 10. So we have 10 times 10 times 10 times 10 times 10 times 10 times 10. So that is 1 million. Now you could simplify this by writing 10 to the 6, but for now I'm going to leave the 1 million there. The kilograms of lead have canceled, and all we're left with is our unit that we desire, which is milligrams of lead. So we just do 0.078 times 1 million, and we get 78,000 milligrams of lead. Let's do one more problem. Convert 7.21 grams per cubic centimeter to kilograms per cubic meter. First, start with what you're given. When you say per, it's like writing the line. Now, we could go with converting grams or cubic centimeters first. It doesn't really matter. It's really just your pick, so I'm going to pick to change grams first. So I'll put grams on the bottom, and I know I need to get to kilograms, so kilograms on top. Now I have to think about which one is larger, so it helps to have your mnemonic handy. King Henry died unexpectedly drinking chocolate milk. And I see that kilogram is the larger unit, so it's going to get a value of 1. The relationship between them is that there are 1,000 grams in a kilogram. Now grams will cancel, and we're ready to convert the cubic centimeters. So in order to cancel out the cubic centimeter, I've got to put a cubic centimeter on top, and I want to get to cubic meters. Now we have to think about which one is larger, and the larger unit is the meter, so it's going to get a value of 1. In order to cancel the centimeters, we have to have centimeters on top, so now those are canceled. Now the relationship between cubic meters and cubic centimeters is not just the same as it's 100 to 1. It's cubed. So to think about this, I actually envision a cube. So think about the cube, and you've got 3 dimensions. Each of those, when they're a meter, make a meter cubed. But when you replace those numbers with the value of a centimeter, which would be 100 centimeters making a meter, it's 100 times 100 times 100, which is actually a million. Now to clean this up, I'd rather write 10 to the 6. Another way to think about this is that the conversion is 1 meter is 100 centimeters, and you just have to cube the number 100. And then you get 10 to the 6. So now we solve by multiplying everything that's on top and dividing everything on the bottom. And the answer is 7,210 kilograms per cubic meter. Happy studying!